So I ended the previous video with this result that the pressure at some depth in a fluid is equal to the pressure above the fluid plus the density of the fluid times g times the depth. So if we have some fluid in an open container where there's some pressure on top, then at some depth d, from with respect to the top of the fluid, then the pressure is going to be P. So that's the pressure one would feel right there. So let's take a look at an example. So I'm going to look at example or exercise, example 13.3 from Knight's textbook, college physics. Where now I've got this container. It's open on one end, but then it's closed on this side over here. So this end is closed, and it's filled with water. So the fluid is water, which has a density of 1,000 kilograms per meter cubed. And so then I fill up this container with water, where this height of this side, the height of the closed end, is 40 centimeters, and the height of the fluid on the open end is now 100 centimeters. And so from our previous discussion, what we said was that if we had a container that was kind of U-shaped and it was open on both ends and we poured liquid into it, then the liquid should reach the same level. It should reach the same level, but in this case here, since one end is closed over here on this side, since we have a closed end, and we just keep pouring liquid in, the liquid can keep stacking up. So the water gets poured in and it fills up on the right-hand side, and then you keep pouring and pouring. And so now I can reach a level which is greater than the other side because there's no way for the fluid to escape on the right-hand side. So the question then is, what is the pressure, P, over here? What's the pressure on the closed end of this container? So that's what we need to figure out. So we can do this. It's not going to be that difficult to work our way through this problem. Because what we can realize is that the pressure on the closed end is going to be the same as the pressure on the open end at the same depth. So we're at this depth right here. So this pressure P is going to be equal to the pressure on the other side. Okay. So to find the pressure on the right side, you basically define the pressure on the left-hand side at that exact same depth. So let's figure out what that depth is. So if we start with the pressure at that depth is the initial pressure pushing down on top of it plus the density of the water times g times the depth. So let's look at the depth first. So the depth is going to be basically this distance here. That's going to be d. So d is our 100 centimeters minus the 40 centimeters to the bottom, which means it's as a depth of 60 centimeters. So d has a depth of 0.60 meters. And then we have to consider what is the pressure on the open end of the container. So in that case, it's atmospheric pressure. It's just the pressure of the air outside. And the standard atmospheric pressure is written as 1 atmosphere, which is a different unit than our pascals that we introduced earlier. But the conversion of that is 1 atmosphere is 1.01 times 10 to the 5th pascals. So it's basically 0.1 million pascals is the standard atmospheric pressure. So the pressure that you feel every time you walk outside your door of the atmosphere pushing down on you here in Buffalo is 1.01 times 10 to the 5th pascals. Okay, so now that we have that information, let's put it all together. So the pressure is going to be 1.01 times 10 to the 5th pascals plus 1,000 kilograms per meter cubed times 9.81 meters per second squared times 0.6 meters. And when you put all of that into your calculator, you should get 1.07 times 10 to the 5th pascals. So the majority of the pressure is due to the atmosphere pushing down on the top of the open container, but the fluid does respond with a little bit of pressure of basically 0.06 times 10 to the 5th pascals. So that's how much pressure is going to be. If we go back and look at the picture, that's what the pressure is going to be on this side right here, which means it's also going to be the pressure on this side, on the right-hand side over here. So that's the advantage of this equation, is that if you find the pressure, you can find the pressure on the open side. It tells you what the pressure is on the closed side because they're at the same exact height. So then one could ask, well, what happens then if we keep adding a little bit of pressure on? So if we have our container filled with the fluid, normally with atmospheric pressure, P0, they say that's 1.01 times 10 to the 5th pascals. But what happens now if I then, say, put a lid on top of this container, and then I push down with an extra pressure of delta P? So what's going to be the pressure down here at some height, or some depth, I should say, a depth of D, like we usually say? Well, I would just have the pressure at the bottom would be this pressure plus the extra delta P. So I'm going to call that P prime. And then P prime would just be P, which is the atmospheric pressure, plus the density times G times the depth, plus an extra delta P, which, you could group together then as the atmospheric pressure plus the extra pressure that you put on the lid, plus the pressure you get from the weight of the fluid. So in the end, the equation is pretty much the same. This is just the pressure on top, which can be either from the atmosphere pushing down, or if you want to do some kind of external pressure where you put a lid on it and then you press down like a piston to try and add more pressure, to increase the pressure inside the container. So one other thing that we can consider Now, as I said, that a fluid could be either a gas or a liquid. So what about this atmospheric pressure? um, so this atmospheric pressure, where is it, coming from? Well, if you're standing on the surface of the Earth, then above you is the atmosphere. So there's all of these nitrogen and oxygen and argon molecules basically sitting on top of your head. And so there is some column of air which is sitting above you, and that has a weight to it. And so the atmospheric pressure that we quoted, P0, as 1 atmosphere, or 1.01 times 10 to the 5th pascals, is due to that weight, that pressure, pushing down on you because we are a couple miles from outer space. And luckily, our planet has a nice, cozy atmosphere to protect us. But at the same time, it does add a pressure, which, our bodies have to contend with. Now, there's one there's one kind of correction that you have to make, and that is the fact that with the atmospheric pressure, there is a large distance, this depth here, d, from outer space down to the top of my head is, sizable. It's, a couple miles, or, several, whatever, tens of kilometers or more. And so you have to take that into account. And so what the correction really that you would have to make is the fact that the atmosphere does not have a uniform density. So therefore, it's actually depth dependent. So the atmosphere is thicker, close to the ground. So it's more dense at ground level, and it's thinner or less dense at the upper atmosphere. And so really to this equation that we have, that the pressure at the bottom is equal to the pressure at the top, plus the weight of the fluid times the basically the weight of the fluid, which is, now in this case the density is dependent on distance. So we'd have to take our density and make it a function of the distance, the depth of the atmosphere. And there's also, and that density, that distance dependence depends on things like temperature and the interaction of the atmosphere. And so really what it becomes is it becomes more of a problem of thermodynamics, in the fact that how the molecules are interacting in a gravitational acceleration, how you're stacking these molecules one on top of each other. And so it becomes a much more complicated problem. So in anything we do in this class, we're going to be just assuming that the fluid has a constant density and not necessarily worry about how the density depends on the depth. To consider the problem of the density, the depth dependence to the density, you have to then introduce some calculus, because it's not a linear problem anymore, and you'd have to do things like integrate over the density, which we're not going to do. So we're going to stick with uniform densities, constant densities for all of the fluids and the problems that we consider.